First, this will be oblique because it's got both an x and a y in it. And yes, this equation right here is in slope-intercept form. So the y-intercept is -3. And the slope is -1. So as a fraction, remember that's -1/1. So we'll go down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. And normally we just connected those four dots together. But when you're solving a system by graphing, which I'll tell you straight up, that's the worst way to solve a system, we need to put as many points as possible on this first line. You'll see why after we get going here, but we want to just keep going with this -1/1. I know it's a pain in the butt to do this, but we want to keep on putting points on this puppy for the first line right here. Did I miss something? No, I'm good. And then once you get them all, then connect them together with your straight edge. So that's the first line right there. Our job is to graph the other line also and see if these intersect in one place, no places, or every place. So it's also in slope-intercept form. Y-intercept of -1, which is right there. And the slope is 1/1. So I'd rise 1, run 1, rise 1, run 1, rise 1, run 1. But remember, what we're trying to do here is figure out where they cross each other at. So if I move up 1 and to the right 1, I'm moving like away from the red line. It's kind of going in the wrong direction here, dude. It's like you want to get close to the red line. So instead of going up 1 to the right 1, you can go down 1 to the left 1, and boom, this is what we're looking for. I got a green dot on top of a red dot. So that's the goal when you graph the second line. Try to get what I call a green dot on top of a red dot. I know you're using pencil, it's both the same color, but this is how many solutions it has. It's got one solution. And we will list that one solution. That one solution is right here at -1, -2. That's where these two lines cross each other at. That's where these guys will be the same at. That's the whole point of solving a system, is where will these two be the same at this particular one point, -1, -2. So let's try it again. Oh no, this guy right here is the first guy. It is not in slope-intercept form. So let's move her way down here, and let's put it in slope-intercept form. That means get y all by itself. First move, subtract 2x from both sides. Those go away, 2y comes down, equals, and then stuff with the x first, and then -6 right here. Then y is not all by itself. We need to get rid of this times 2. So we'll divide everything by 2. And that would be -1x, which we can just write as -x, -3. So here's that first line. Let's graph it. Start down here at -3 and go down 1 to the left 1, down 1 to the left 1, down 1 to the left 1, and keep going. That first line that you want to graph, you want to put as many points on it as possible. The reason why we do that is because there's human error when we put our straight edge on here and we try to connect the dots together. It's like if your straight edge isn't lined up perfectly enough, then the line gets off and you can't really tell where things intersect each other at. So we want to put as many points as possible. Then to graph this second line, whoa, it's the same thing, right? These two guys right here are the exact same line. So I'm done already. So since it's the same line on top of itself, that means that there are infinite solutions to this, dude. Infinite solutions. But you know, we're going to do something really cool. We're going to put the college algebra answer. Yeah, I said college algebra, what you do in college, as compared to what we're just doing here. It's not like there are really infinite solutions. I mean, there are, but there are some answers that just don't work. Like we're trying to list ordered pairs that work in this situation. Look at this ordered pair, 0, 0. It's not on that line at all, right? So even though there's an infinite number of solutions, we want to list all of them that work as an ordered pair. So here's what we're going to write. Infinite solutions in the form, and then we're going to list the ordered pair that they work. And it seems kind of weird at first, but here's what the ordered pair would be. First, you just let the x value be x. And then the second one, instead of putting y, doesn't y equal -x minus 3? So we're going to just put that in the place of y. Instead of putting the letter y, you pick an x value, and then we can figure out what y is. Just like if x was 0, right? Then y would turn out to be 0 minus 3, which is negative 3. So they're saying 0, negative 3 is one of the solutions. If you let x be 1, then 1, negative 2 would be a solution. So there's an infinite number of solutions in the form of x, negative x minus 3. Moral of the story, how do you write this answer? This guy will always be x. This guy will always be what y equals. We have that in slope-intercept form. We know what y equals. You just throw that in your y value part right there. So, holy macaroni. First guy is in slope-intercept form. Let's graph it. Slope y-intercept of negative 3, slope negative 1. Put as many points as you possibly can on there. And I might move a little fast for you. You can always pause the video, but there's the first line right here. Second line, going to be oblique also. It's got both x and y, but we need to get it in slope-intercept form, so first move is to subtract 2x from both sides. Those go away. 2y comes down. And then we got to divide everything by 2 to get y all by itself. Let's go away. Negative 1x plus 2. So to graph that, y-intercept of 2, down 1 to the right 1. And I can tell already, just by looking from the red line and the green line, that they're never going to touch each other because they have the same slope of negative 1. You still got to end up graphing both lines, but this has no solutions because these guys never crossed each other, so there are no solutions. And then you tell me why. It's because they were parallel lines. Then you tell me how you knew that. Because they had the same slope. So we put both of them in slope-intercept form, and they ended up being parallel lines to each other. So because they had the same slope of negative 1 both times. Let's keep moving. We got to put both these in slope-intercept form. Why don't you pause the video and get both of these bad boys in slope-intercept form? So here's my first one, right? I got y equals negative x minus 3. Well, we've graphed that enough today. And then I'm going to plot the second one after I put it in slope-intercept form by subtracting 3x from both sides. And y equals negative 3x plus 3. So start at 3, go down 3 to the right 1, down 3 to the right 1, etc. And boom! I wanted to get a green dot on top of a red dot. So I got that right there, meaning that there is one solution to this puppy. And it is at this particular ordered pair of 3, negative 6. We're solving systems by substitution here. This is lesson 6.2. And solving systems by substitution is a way better method than solving by graphing because it's all algebra involved and we can get an exact answer. Solve by graphing was just an approximate answer. So when do you solve by substitution? Obviously when they tell you to, and when you have a variable all by itself on one side of the equal sign in one of these equations. It just so happens on number 1 that we have it in both equations, but the idea is we want to try to find where these two values are the same. Like if we did graph them, where would these lines intersect at? So here in this top equation, we see that y equals 5x minus 25. Since y is all by itself, we can put a box around 5x minus 25. And in the other equation, we can totally substitute 5x minus 25 in for y. So I'm a fan of putting this box around this information and putting parentheses around what that information equals in the other equation. So it's kind of weird at first. Just hang in there and let's do quite a few examples. So I'm going to take what's in the box and put it in the parentheses. And since the number in front of y here, there is no number like right here in front of y, we don't even really need the parentheses. We're just going to say wherever there was a y, we can put 5x minus 25 in. So 5x minus 25 went in for y right here. Then I'm just going to copy the rest of this equation down. It equals a negative 8x plus 27. So this equation right here, I can totally solve for x. The x's, there's more than one. They're on different sides, so I will add 8x to both sides to get them on the same side. It doesn't matter which one you take over to what side. So 13x's minus 25 comes down, equals comes down, and those went away, and 27. Then we will continue solving by adding 25 to both sides. And 13x equals 52. And then we'll divide by 13, and x turns out to be 4. That's half of our answer right there. We were looking for the ordered pair where these two lines intersect each other at, so we know the x value is 4. Now to find the y value, we will just substitute 4 in for x into either one of these equations. It really doesn't matter, but I like to substitute it back into the box. So, and we'll do a little bit of mental math. We're putting 4 in for x, so 5 times 4 is really 20, and then the rest is still there. And then we can simplify that and say y equals -5. So there is one solution to this system, and it is at 4, -5, if I could write correctly. And we'll put that ordered pair in the blank right there. So let's try it again. We need to have a variable all by itself on one side of the equal sign. We have two situations, so 21 minus x will be going in for y into this other equation. So let's do that. 21 minus x equals 3 plus x. And then we'll get our x's on the same side since they're on different sides. So I'll take the smaller amount over. Doesn't really matter. 21 comes down. Equals comes down. And x plus x is 2x. Then I'll subtract that 3 from both sides. And get 18 equals 2x. And then we will divide both sides by 2 and get x equals 9. So there's half our answer. Now I can substitute this into either equation. This one would probably be easier because it's just addition. So y equals 3 plus 9, y equals 12 in that situation. So ordered pair, 9, 12 is where those two lines would have intersected. And you can see that on our normal graph we don't even get up to 12 in our, because we always just go up to 10 or something. So it's very nice to see where those intersect at. Y is all by itself, so I can put a box around this and substitute in. And it looks ugly because of the fractions, but I'll show you a cool trick once we get this all substituted in. First move is to substitute. Then, I don't like fractions any more than you do, so we will clear the fractions by multiplying through by the least common denominator. I have two different denominators of 2 and 4. Show you what the least common denominator is, again, concept-wise. If you start writing out multiples of 2, and then the other denominator was 4, if you start writing out multiples of 4, you just want to find the smallest number that's in both lists. Well, that's 4. So that's the least common multiple between those two. If we multiply both sides, or I shouldn't say both sides, if we multiply everything times 4, that's going to clear out the fraction. So it's just a cool distributive property. This is a divide by 2, so you got to ask yourself how many times does 2 go into 4 evenly, and that's twice. Take that result times the numerator and you get a 2. And there was an x with that. We also need to take 4 times -5 and get -20. Equals comes down. Then we got to take 4 times this guy. There's a divide by 4 in it, so 4 goes into 4 once. Take that times your numerator, and you get a -3. And there was an x with it. And we also have to take 4 times 10 and get a positive 40. Now this red equation is much easier to solve than that green one. So we will solve it. Let's get all our x's on one side. (5x minus 20) and then add 20 to both sides. And then divide by 5, and x equals 12. Now that x equals 12, we can substitute that back in. Doesn't matter. This one would probably be easier because the fraction in front of x is just a half, and we can take half of stuff real easy. We can do that in our head. We want to take half of 12, which would be 6, and then there's the minus 5 there, so y equals 1. So ordered pair of 12, 1, right there. Now we're still solving systems by elimination, a little more complicated. We still have all our terms lined up, x's on top of x's, y's on top of y's, equal signs on top of equal signs, and constants on top of constants, but I don't have that set of opposite coefficients. Like, if this is a 5x, that's not a negative 5x, and if this is a negative 2y, that's not a positive 2y. So what we got to do is just manipulate one of these equations to where we can get some opposite coefficients. So like we said, if this is a minus 2y, I'd love for that to be a positive 2y, so I can do that very easily by taking that whole top equation times 2. So I'll do that, and I'll just put my little answer right here. I'll take 2 times x and get 2x, and 2 times y is 2y, and equals is still there, and 2 times negative 9 is negative 18. Then I'm going to get rid of this brother. Now I can add these two equations together and get a variable to cancel out. The y's will go away. So I'll have 7x equals 32, and a negative 18 is 14, and then that means x equals 2. And that means I will have a solution because there's still a variable left with this. There'll be one solution to this. We'll find that solution by putting 2 back in for x into any one of these equations. It doesn't really matter. So I'll put 2 in for x and get a 2 times 2, my bad, is 4 plus 2y equals negative 18. I just put 2 in for x right there. Now I will solve. Subtract 4 from both sides and get negative 22, and then divide, and y equals negative 11. So here's our one solution. It's at 2, negative 11 for an answer. Here we could cancel what we want to. It doesn't really matter. Let's cancel the x's just for fun. So if this is a negative 2x, I'd love for that to be a positive 2x, so I'll take that whole top equation times 2, and I will get 2x minus 2y equals negative 2. And this goes away now. I like to cross those out when I only do a single manipulation, right? I've only changed one equation, so let's add these together now. X's, negative 2x and 2x cancel each other out, but holy cow, 2y and a negative 2y, they also cancel each other out. There's absolutely nothing left on the left side of the equal sign, so we put a 0 there. And then when we add these together, negative 2 and a negative 2 is a negative 4. So you see how all the variables disappeared. X's went away and the y's went away. That means that one solution is out. So we have to realize, is it going to be no solutions or infinite solutions? Well, you ask yourself this question. Does 0 equal negative 4? Yes or no? And that's no, so the answer is no solutions to that system. Cool. Let's try number 6. Let's manipulate. Let's go ahead and cancel the x's just for fun. It doesn't matter which one you cancel. You cancel whatever you want to, but if this is an 8x, we need that to become a negative 8x. So I'll take that whole top equation times negative 4, and that will make it a negative 8x. So I'll get negative 8x, and then negative 4 times negative y is a positive 4y, and negative 4 times negative 1 is a positive 4. I'll say goodbye to you, and I will add these together now. X's went away, and so did the y's. So you're left with nothing over there, and a negative 4 and a positive 4 add together to be 0. So one solution is out because all the variables disappeared. So I got to ask myself, does 0 equal 0? Yes, it does. So that means that there are infinite solutions. And then we need to do that cool college algebra answer in the form of, and the problem is we have to take one of these equations and get y all by itself so we can answer that cool college algebra way. So I'm going to take this dude and put the whole thing right here. That was the original guy. Now I'll get y all by itself. So I would subtract 2x over. There'd be a negative y still there, and that'd be a minus 2x minus 1, and then I just got to change all the signs because I don't care what negative y equals. So now I got y all by itself. There's infinite solutions in the form of x, comma, whatever y equals. Well, y equals 2x plus 1.